for section 12 is all about isomers. Now, we've already talked a little bit about isomers. Specifically, in previous sections, we've already covered geometric isomers and the two types of optical isomers, enantiomers and stereoisomers. But today we're going to kind of tie it all together and look at it in this flow chart. Now, your outline does not have all of this written in, so if you want to pause the video as I go through, you can definitely do that and write it all in. Okay, so just as a refresher, when you have molecules and they're isomers, it means they have the same molecular formula. Okay, constitutional isomers versus stereoisomers. So these are kind of the two broadest categories, and then we get into subcategories below those. Constitutional isomers, of course, have the same molecular formula because they're isomers, but their atoms differ in connectivity. In other words, the atoms are bonded to different partners, if you will. Okay, so different atoms. So here I have an example to kind of help us visualize it. If I call this carbon 1, this carbon 2, this carbon 3, this carbon 4, 1, 2, 3, 4. Okay, well, actually let me label these in terms of chemical equivalents because that's really what we should be doing. So I will call this carbon A, this will be carbon B. This carbon right here is chemically equivalent to carbon B. It's in the same environment, and so it is also a carbon B. It can be labeled carbon B as well, and then this last methyl group is identical to carbon A, so it can be labeled carbon A. So here, for the bottom molecule, this would be carbon A, this would be B, A, and A, okay? But by looking at these two molecules, we can see that they have the same number of carbons, they have the same number of hydrogens. The only difference is which atoms are bonded to which other atoms. They differ in connectivity. It's kind of as if this methyl group right here was taken off and bonded over to this carbon. That's kind of the transition from the top molecule to the bottom molecule. Okay? So, constitutional isomers, they relate to each other by having different connectivity. Now, stereoisomers, on the other hand, they actually have the same connectivity. The only thing that differs between the isomers is their arrangement of their groups in space. Okay? So, a carbon is still bonded to the same carbon as it was in its isomer, only maybe instead of going behind the page, it's coming in front of the page, or vice versa, okay? So they have groups that have the same connectivity, but differ in arrangements in space. Okay, so there are then two subcategories of stereoisomers: conformational isomers and configurational isomers. And the biggest difference between these is that, well, the difference between them is that conformational isomers can be converted to each other just by the rotation around a sigma bond, whereas configurational isomers, unlike conformational isomers, cannot be converted into the other isomer just by rotating around a sigma bond. So in other words, let's look here in green, the conformational isomers. Here is an example. We have this butane molecule, and here we have another butane molecule. The only difference is if we rotate around this sigma bond, we will turn into this bottom isomer. So really they're the same molecule. The only difference between them is the rotation about that sigma bond. And because of that different rotation around that sigma bond, it will put the different groups in different spatial arrangements depending on that rotation. Okay? Configurational isomers, on the other hand, they're stuck. Okay, there is no rotation for one reason or another. and so the spatial arrangement is stuck. So let me show you the two types. Okay, there's geometric isomers and then there's optical isomers. Both of these types are configurational isomers. Now the difference is, for geometric isomers, the reason why you can't interconvert between geometric isomers is because you have a rigid bond. Okay, either you have a ring structure, so you can't rotate around single bonds because they're part of a ring, or you have a double bond, in which case you can't rotate because of the pi bond that you have. Sometimes geometric isomers are called Sis Trans Isomers as well. And here's an example of a Sis Trans isomer, specifically the double bond, okay, where we have a cis version and a trans version. Now, optical isomers, and there's enantiomers and distereomers, their arrangement of their groups differ in space, but it's because they exist at a chiral carbon. Not necessarily, it doesn't matter if you can rotate around all the single bonds you want. It doesn't matter because they're all bonded to that central point, which is a carbon, okay, a chiral carbon. So enantiomers are non-superimposable mirror images of each other. And here in purple I have drawn an example. Now distereomers, which I didn't draw an example, but I'm sure we'll see some down in our practice problems, they are non-superimposable and non-identical. And we did have a previous video over this. It's really kind of the catch between, well, we can't call these identical because they're not identical all the way through with all of their chiral centers, but we can't call these enantiomers because they don't have a mirror relationship at every chiral carbon either. And the one thing that you want to really remember about distereomers as well is the fact that you need at least 2 chiral centers even to be distereomers, even to have that as a possibility, okay? So really, the thing about these definitions is you just have to memorize them. Okay, so practice will help making flashcards, but at the end of the day, you're just going to have to memorize these terms and their definitions.